So this unit, it's about simple harmonic motion. It's a very short unit in this course. There are two equations that we should know, and we're going to write them down. So there's one equation for pendulum. There is another equation for spring, and I'm pretty sure you have seen it. I'm not sure if you have used it in class. So for pendulum, it's L over G. M over K is for the spring. And I believe that you did some lab activities regarding to spring and some pendulum moving at an angle. Yes? Okay. So what did you discover? Did you discover anything during the lab? You don't think so? All right, now, so we'll first talk about pendulum. So first, what does the big T stand for? Nope. Time, or specifically period. Oh, right. Period. And one thing that is closely related to period is frequency, which is basically 1 over T, or the reciprocal of T. Okay. Now, since you all are in pre-calc, so you would actually have some advantage, okay, to understand period in a moment. So review. Now, before we go too deep into this topic, let's just think about a very standard situation that, you know how we have those pendulum clocks, okay? So it swings back and forth, and we assume that it swings one way, it's going to be 1 second. So one way, it's 1 second. So coming back, it's another second. So in that case, we'll call this period for the pendulum, a total of 2 seconds. Okay, so when we say a period, like in pre-calculus, the sine graph and cosine graph, we're talking about a complete cycle. Okay, going forward, and it has to go backward. So that's 2 seconds. Now, so the first challenge for you is this. If we know the period, it's 2 seconds. Could you find out the length of the string? Okay, could you find out the length of the string? Okay, for the pendulum. Okay. Now, one thing that you should realize when you are looking at these two equations is that the thing that is really controlled by us are in the numerator, the mass for the spring and the length of the pendulum for the pendulum. Okay, all the other ones are basically constants. So we say, hey, 2 seconds, right? So that's equal to 2 pi. And then L over G, which is 9.8. Okay. All right, so if you have a calculator, I'll let you calculate it. As you type your calculator, now, this is what I would advise you to do. This is just me being a math teacher. We should always simplify things before we put it into the calculator. Okay. Now, if you say I didn't do it, is it going to be a problem? Well, probably not. But then when you type into your calculator, I would hope that you would type into your calculator like this with a pair of parentheses around 2 pi. Because if you don't type this pair of parentheses, if you simply type 2 divided by 2 pi, your calculator would think that the 2 is divided by 2, which is equal to 1, and then multiply by pi. So that's one reason I would suggest people to just simplify before you type into your calculator. Okay, so 1 over pi, and then you square it, and then times 9.8, and you should get the answer 0.993, and the unit is in meters. Okay, cool. All right, so far so good. Now, so as you can see, the calculation, it's not that hard, and for the most part, it's not really that hard with regards to these two equations. Now, when we talk about pendulums, which is our first topic here, we always love to ask a couple of things. So we're going to see these questions in just a moment. Now, as you know, the pendulum goes forward and backward, and it passes through the center, right? Let me go ahead and make this a little bit more symmetrical so that it makes me more comfortable. Okay, so it goes back and forth. All right, now, physics teachers will always love to ask this question. Can you label these accelerations and velocities? There are two choices, 0 or max. Okay, where is the velocity 0? Where is velocity the maximum? Where is the acceleration 0? And where is the acceleration maximum? Okay, so let me start with the easy question. Where is the velocity 0 for the pendulum? And the sides, right, at the ends of it. So let me go ahead and put down 0 for those velocity. And since the sides have the minimum 0 velocity, so the middle must be the maximum. Okay. And then what about acceleration? 0 in the middle and max on both sides. Okay. All right. Any question you want to ask? Does that make sense? Yes? All right. So, I got a question. If there's any acceleration, that means there must be a net force. Who is contributing to the acceleration? What is contributing to the acceleration right here? What is contributing to the acceleration of the object when it's at the end? The what? The weight, yes, the weight, indeed, the weight. Now, because the weight, it's going straight down, but it's not the motion of the, it's not aligned to the motion of the direction of the motion. So we would have to break it down to the two vectors, okay? So we're gonna break down this vector, and we're gonna break it down to this vector, the horizontal and vertical vectors. Now, in case you wonder, we are going to label this as our angle theta. Okay, I think you did your experiment, you measure your angle theta, right? And that is your angle theta as well. So the force, which we actually have a name for it, we call this particular force the restoring force. Well, it's the weight, but it's the weight at an angle. So we call this restoring force mg sine theta. Sometimes you may see it with a negative, depends on the direction, but the magnitude of it is mg sine theta. Why do we do this? I mean, it's still, I would say it's still part of the conservation of energy umbrella. We will see some questions like those. Like, yes.
But last year, all the FRQs were about
Oh, really? Oh, we have to take a look. Yeah, supposed to be easy. And also it could embed, you can squeeze in other stuff into this topic. I mean, we're going to talk about conservation of energy in a moment. And you can think about how the pendulum could swing from one end to the middle, and then it's going to hit another object, so we can combine it with momentum. Okay, so that's why I would say put it into the big umbrella of energy unit. So, all right, so that's the restoring force, and it's going back and forth. All right, now here's another question that we all love to ask. If you change the bob to something more massive, would the time it takes to swing back and forth change as a result? Okay, I've got a little makeshift pendulum right here. Okay, so so I got this cup as the bob of the pendulum. Okay, so it can swing back and forth like this, the cup. And then I got a little protractor, which is very light, small mass. And then swinging back and forth. So if the theta for these two cases are the same, would the period be different if the masses of these two objects are different at the end of the string? No, meaning they won't be different. They will be the same, right? How do you know they will be the same? Yeah, the equation does not have anything in mass. That's good. And if you are just curious about this, I mean, that's how you can take a look. They move together. I mean, you may suspect that is it because one is moving slightly slower, but if you look at the equation, there's no mass in it. So so period does not depend on the mass of the bob. Okay.